Hi
Hi
everyone.
everyone.
So my
So my name is Oscar Van Rest. I'm a developer of Oracle Property Graph Technology at Oracle. And this presentation is about the SQL extension for property graphs. And these slides are built on top of a previous presentation from one of my colleagues, Jan Michels, who is the chair of Insights Data Management and DM32 SQL PGQ Expert Group. So what I will cover in this presentation is what is the SQL standard, what is SQL PGQ, what are the capabilities of SQL PGQ, and possible future extensions. So first of all, what is SQL? Well, I think most people know it's a well-known Azure database language standard. It's an ISO standard, and the number of the standard is 9075, and it's developed in collaboration with various national bodies. It has 11 parts. So the first 3 parts, framework, foundation, schemata, is the core of SQL. So it defines like the basic like select, from where, DDL, DML. And then there are 8 additional parts. For example, for JSON, for XML extension, and then most recently PGQ, which stands for property graph queries. So even though the first version of SQL came out a long time ago, 1986, there have been various revisions over time. Roughly every 5 years, there's a new revision where additional features are being added. And the most recent version is SQL 2023. So the versions, they correspond to the years in which they are released. And yeah, the biggest new part of SQL 2023 is the property graph queries. So there's many implementations of SQL with various degrees of conformance. So every implementation implements a somewhat different subset of SQL because it's impossible to implement so many different features. And there's a large number of applications. And I guess it's fair to say that SQL has withstood the test of time. So why integrate property graph with SQL? Well, a lot of data in the world is already stored in relational databases. And you can see tables as modeling a set of vertices or a set of edges. And the columns in the tables you could see as properties of the vertices and edges. And in this way, you can essentially reuse all the existing SQL capabilities for graph use cases. So there's no need to duplicate functionalities such as group by, row pattern matching, window analytic functions, or the security model. All these things can be reused for graph queries. So for example, you can grant read access to a graph or things like that. And transaction, metadata, all these things can now be reused for graph queries. Furthermore, a big thing is also that you can easily join graph data with relational data. So use cases may like to do some parts using graph queries, other parts using more traditional SQL queries on tables. And if you have one language that allows you to basically combine graph data with relational data as well as other types of data like JSON, you can do various other things. So what is SQL PGQ? So SQL PGQ is the extension of SQL for property graph queries. And it's the 16th part, so that's why we have a 16 here of SQL. So in SQL PGQ, property graph is a first class database object. Just like in SQL, we have views and tables, which are first class objects. And a property graph is a view-like object. So when you create a property graph, it's not going to duplicate all the data that is already in your tables, but instead it's like a view on top of your tables. And using data description language, you create a graph on top of tables using this create property graph statement or drop property graph statement. And yeah, tables hold a set of vertices or edges. No restrictions on number of vertices or edge tables or number of graphs in your database. So each schema can have any number of graphs. And then once you've created a graph, you can query it inside a SQL statement, inside a select statement using this graph table operator, which sits in the from class of SQL. And yeah, as already mentioned, SQL PGQ, it defines a data model, it defines the DDL for creating a property graph, as well as, for example, altering a property graph. And then it has a graph pattern matching part to it, which I will show in the next few slides. So in the next few slides, I'm using some example which is anti-money laundering, as most of you know is one popular use case for graphs. So this is the sample data we'll be using. So we have accounts, customers, owns, transfers. So accounts and customers are typical vertices, and then owns is an edge that goes from customer to accounts, and then transfers is another edge that goes from one account to another account. So given those tables, this is how you can create a graph on top. So you say create property graph, AML. So this is just the name of the graph, anti-money laundering. And then you have a set of vertex tables and a set of edge tables. So here we have two vertex tables, accounts and customers. And then we have two edge tables, owns and transfers. And as you can see, the owns edge table goes from customers to account. This is not saying anything how exactly these two tables relate because it's using underlying foreign key. So you don't have to specify that because it can reuse that information that already exists on the underlying tables. Whereas here for transfers, we do specify a key for the source and the destination, because in this case, we cannot use an existing foreign key. And other thing to notice, so accounts as account, this is just an alias. And here we don't specify a label, so the alias is used implicitly as a label, whereas here we do explicitly define a label. So here the label is customer, and again here we don't specify, or here we don't specify a label, so the label will be owns. For this one we do specify a label, which is transfers. And then properties, by default, all the columns in the table become properties of the vertices or edges. So here we don't specify properties, so all columns become properties, whereas here we specify 3 properties, so if the table has more than 3 columns, then only these 3 columns become properties. And here for the edges, we for this edge transfers, we only have 2 properties, one an amount. So this is just kind of repeating what the last slide already said. So we can build graph on top of existing tables, customer accounts, owns, transfers. And then user can specify 1 or more label per table, 0 or more properties per label. Each vertex and edge has a key, which is either composite or not non-composite. And then all kinds of defaults apply, so you don't have to specify a key if there's already a primary key in the table that you can use. And you can mix and match, so you can use defaults when possible to keep your statements short, but there's always explicit options available too. So this is the same data we saw before in tabular format now in visualized as a graph. So that's the 100, it's a customer, whereas the one starting with an A are the accounts, and then we see there's transfers between accounts and the customers own the accounts. This one is just colored red because in this network, this is like a fraudulent customer that we are maybe trying to get some information about. So here's a first example query, a select query, where we see the new graph table operator, which sits in the from clause, alongside possibly other table expressions in the from clause. And in this case, there's only one table expression. And then the graph table takes a name of a graph as input, so AML, anti-money laundering graph. And then we have a pattern match, and then we have a projection. So this query projects 4 columns. And what this query does is it retrieves the info of all customers who got more than $10,000 from a customer 100 with ID 100. So here we see, for most people familiar, graph pattern matching syntax, where we have vertex patterns with parentheses and edge patterns with the square brackets. So this is matching a customer C1 who owns an account, and that transferred to another account and owned by customer C2. And we look for transactions with amount greater than 10,000. And then the output of this query is just a regular SQL table with rows and columns. So as mentioned already, we have vertex patterns and edge patterns. Vertex patterns I mean, and this is using SQL, as most people are familiar with. So vertex pattern has 3 optional components: variable name, label expression, and where clause. So here's examples of vertex patterns. So if we just focus on the one here on the bottom right, we see here C is a variable name, its customer is a label expression, and then we have a where clause. C.first name is Joe. And you can omit these various parts of the vertex pattern. For example, if you omit the label expression, then it's gonna match a vertex with any label. And for adds pattern, it's pretty similar. I mean, they use the square brackets and pointers to say if they point, if they're outgoing or incoming, or in this case, any directed, which means incoming or outgoing. And they again have 3 optional parts that go between the square brackets. If you don't have any optional parts, then you can also leave the square brackets out. So here again, if we look at this example here, we have a variable name, label expression, and then an optional where clause. So now you can combine these vertex and edge patterns to form a more complex pattern. And the patterns can be quantified, which means that that they have like this POSIX quantifier, which is either a question mark or this n means exactly n to m means between n and m. So this allows you to match a pattern in a repetitive way. So you can match arbitrary length patterns in this way. And these quantifiers can be placed on individual edge pattern, but it can also be placed on a more on a parenthesized tab pattern consisting of multiple vertices and edges. So these 3 quantifiers here, they allow you to match. They don't specify an upper bound, so that means they can match any number of edges, which can be dangerous because if the graph contains cycles and you say, okay, 0 to any number of iterations, it may cycle forever. So that's why the query language puts certain restrictions in place to make sure that queries are always guaranteed to terminate. And I'll show some more about those restrictions later. So here's another example query. So this query retrieves all info of customers who got more than $10,000 from customer 100 via one intermediary. So it goes from C1 to a customer C2, and it has 2 transverse edges, both with amount greater than 10,000. And then you see here we get some info from the customer C2 as well as the amounts of the 2 transfers. And then this GT, it's an optional alias, and then if you have perhaps multiple graph tables in a from clause, you can easily identify the different columns. Since we select all columns, you could also have set select star and it will give you the same result since it's the exact same number of columns as we see here. And then again, you get this table out. And then let's see another example, this time with a quantifier. So here we're matching this edge 1 to 4 times. And since we don't specify anything like shortest, or it means that the default is that we find all path from C1 to C2 where this edge is repeated 1 to 4 times. And we're starting the search from customer with customer ID 500. So this is going to find all the customers C2 can be reached from the customer 500 within 4 hops. And this is kind of built on top of the previous query. So now we again say 1 to 4 hops, but this time we introduce this variable T1. And because this variable is within this quantifier, it means that it may match to multiple edges. And therefore you cannot simply use it in the columns clause like we do with other variables. Like C2, you can directly access a property. But since T1 binds to multiple edges at once, you have to place it inside this aggregate. And you can use any aggregate. So here we just use count to count the number of edges along the path. But you could also use other aggregates like min, max, or list ag, JSON array ag to get all kind of information from the edges along variable length path or vertices along a variable length path. And then here, so we find multiple paths, and then for each path we get the length of the path, number of hops, and then we group by customer to get the minimum number of hop of some of the paths that were found. So this is essentially computing the closest distance from customer 500. I think as some of you may already think, okay, why not use shortest path to compute distance? So this slide is essentially doing something similar, but using this keep any shortest. So this time we're looking for cyclic path starting from C1 back to C1. And because we are using keep any shortest, we can now use a cleany star because we know that the number of paths will be limited. And then here at the bottom, we count the number of hops along the path. And here we're simply using an arbitrary property of T1. You could have also used the vertex ID or edge ID, vertex ID or edge ID, I guess, or some other expression that somehow involves T1 in order to use an aggregate like this. And this time we can directly access the min hop without having to do another group by. Let me check. Okay, and then we have path selectors and path restrictors. So together, these two decide what type of path you find. So you always pick one of these and you pick one of these and combine them. And if you don't specify one, then the defaults apply. So for example, you can find any trail or shortest 10 acyclic path. And the path is just an optional keyword that comes at the end. So you can use any of these in combination with any of these. And with certain restrictions, for example, if we have a cleany star, then you cannot use the all. And then finally, this so I've already showed that using these aggregates, you can access data along variable length path. But there's another way, which is one row per vertex, one row per step, which essentially unnest a path, so it has a shortest path. So you can, for example, say for each vertex along a shortest path, or for each step, which is a vertex adds vertex triple, along a shortest path, give me a separate row in the result table. So this is the final example I have where we start from customer C1 and again go back to customer C1 via one or more transverse edges. And we keep all simple paths. So a simple path is a path that doesn't repeat any vertices other than possibly the first and last, since we do want this C1 to be the same as this C1. And then we start from customer with ID 500 again. So this where clause comes after keep clause. If you want to have pre-filters, you can specify them before the keep clause. In this case, it doesn't matter. The outcome is the same no matter if you specify this filter as pre or post filter. But that's not generally the case. And then, yeah, we do this one row per step. So now for each path that we find, we're gonna go get one row for each step. And a step is essentially an edge and its two endpoints. And then we can get information for the vertices and edges along those steps. And to show you an example result, so this is the result of this query on the example data. So we can see that we have found 5 paths. So the first path has 2 transfer edges, second path has also 2 edges, and then third path has 3 edges. So this is how you can retrieve data along path as an alternative to using the aggregates. So there's a couple ideas for future extension to SQL PGQ. And these are just ideas and sometimes initial write-ups. And I mean, hopefully they will end up in the next SQL version, which may only be there in a few years. But this is all still, so some of these are just ideas and nothing more than that. But yeah, one of the ideas is to add additional path selectors, such as cheapest path, minimal path, maximal path finding. Conditions that cross iterations of quantifiers. So this is, I think, especially useful for LDBC financial benchmark, because I understood there we sometimes want to find path of transaction edges where we want the timestamp to keep increasing. Otherwise, it's not a valid path. So currently, you can only specify that for each, let's say, adds on a path, you can specify a filter, but sometimes you want to specify a filter that applies to each 2 consecutive edges. So that's something we hope we can add at some point, and as well as optional pattern matching, which is essentially like left outer join, as well as exporting of vertices edges path into JSON. So thank you. This was my presentation. I want to mention one more thing, is that my colleague Damien Hirulin will also give a talk tomorrow about combining graphs and large language models, in case any of you is interested in learning more about the work we do at Oracle. And yeah, please let me know if there's any questions.
Hi, Oscar. This is Robin from Alibaba, and I have a couple of questions. So I'm wondering if SQL PGQ has been widely adopted by end users or the users from Oracles, and if yes, then this is case and how users react to it. Do they have any feedback, either positive or negative? And I'm asking this question because recently we have submitted a paper describing how to optimize SQL PGQ, and the reviewer left a message for us saying they would rather see us optimizing conventional query by implicitly using graph feature instead of explicitly writing like SQL PGQ, and how do you react to that? Thank you very much.
Okay, so first part of your question, I mean, we've been working on graph technology for a while already, but initially we had a separate language before we integrated it with SQL. And since Oracle 23 AI, which is the latest database release, we now support SQL PGQ. Not all the features that I've showed on these slides, but a subset of these features. And this is still pretty recent that this became available to customers. In the cloud, in Oracle Cloud, you can use it. And there's also Oracle Database free release that uses it, but on-premise, it's not GA yet. So most people that use it right now are people in the cloud. And it's still, yeah, it's still kind of a initial feedback. So it's not too much yet. I mean, it's mostly about features that we plan to implement that are already in the SQL standard that they want us to add, and not necessarily additional features yet. But I do think that the general, yeah, the people are very happy with that they can just use Oracle database that they already have installed, and they already have their data in relational data tables. They can just use Graph on top, because previously our solution required to install a separate server for Graph, and they need to synchronize between Oracle database and that server. And it was just a lot more complicated. But I think people are very happy to switch to this new approach, but it will take some time. And then, yeah, your second part of your question, I kind of missed.
So there's one reviewer say, they would rather, because we try to optimize SQL PGQ, and it left a message say they'd rather us, we can optimize conventional query using graph features instead of, explicitly write SQL PGQ. I think it's come from the compatibility issue, because, they would rather not changing any of their query language at the beginning, right? So I'm wondering if this is true on your side, and how you react. Do you have any feedback for this? Thank you.
Yeah, I mean, I guess optimized, like from a customer perspective, I guess like there's like all kinds of hints and all at Oracle that you can do to optimize things. But with the things we add with Graph, we are really building new features on it. So it's not just like translating to existing SQL, but for example, for shortest path, it's like new type of operation. So this may come with its own set of optimizations. I mean, maybe there will be other types of hints, for example, I'm not sure. So yeah, there will be new challenges, but yeah. I think I think so far it's possible to apply the same kind of techniques that we did for tables also to graphs, and that the optimization techniques can be reused, I think.
Oscar, can I just make a comment about the presentation? Oh, is that not working?
Yeah, sure.
Sorry, can you hear me? Yeah, I just want to make a comment
Yeah,
about
hi.
the presentation.
Hi,
Because it's the second time I've seen it presented. I think there are two things that are quite important to emphasize. One is the little bit of query language in red that's in the middle of these graph table examples that's being shown is shared with GQL, right? That it's exactly the same language, the graph pattern matching language. And I think that that's related to my second point, which is the presentation doesn't make it completely clear that these graph views are not updatable views. There's no language, there's no mechanism for updating the graph other than updating the underlying tables. And that's not meant as some fundamental criticism. I think it's a great presentation about the many advantages, and I really like the point about putting a graph on top of the existing data and not moving the data. I completely see that. But I guess it relates to the point about the future, because in the future, it feels to me like more of GQL is going to have to come into SQL, because people are naturally going to want to update their graph views using DML. And it's likely that there's going to be a desire to have a more sort of standardized view of schema, of graph types that would actually be shared between the two languages. I mean, that's my personal view, that that's almost going to have to happen. I also think it would be desirable, that there's nothing good about there being a big gap between SQL PGQ and GQL. It would be better in the long run if these two languages were more and more convergent. I just wanted to emphasize that point. I know that may not be popular in Oracle, but it's my view.
No, I mean it's true. I mean this match clause and basically the things inside the graph table are almost more or less the same between GQL and SQL PGQ, and I think this benefits both languages, and that's definitely true. And yeah, the thing about updatability. So indeed, right now, if you want to update your graph, you apply the updates to the underlying tables, and since the graph is a view, it becomes visible in the graph. Yeah, perhaps in the future, indeed, people may request graphs to be updatable through graph updates, specialized graph update, but at least right now, that's not our main focus. I think there's still a lot of work left, like the things mentioned here. That is the more important, and we also need to see. We actually need to get feedback from customers and also maybe get feedback from other companies and see how much interest there is in having specialized graph DML, or if people are maybe already happy with just applying updates to underlying tables, because it's also not entirely clear how to do it. For example, if you insert a new edge, then which table should it go to? Because two tables may have the same label, so it's not entirely clear how this would even be done. And but first, yeah, foremost, I think we need to focus on other features first, and then see how much interest there is.